Hello and welcome. In a series of previous videos, we've taken a look at different techniques for integration. Depending on what you have in the integrand, sometimes you can get away with just a substitution. Sometimes you have to use integration by parts or partial fractions or maybe some kind of more clever substitution like a trigonometric substitution. But you don't have to go searching very far in order to find examples of integrals that you can't evaluate using any of those strategies. Now, what are you going to do if that kind of situation arises? Well, we got to remember that if you have a definite integral, something where you're just integrating from x equals a to x equals b, let's say, then you can always go back to just the good old definition where we take the limit as n goes to infinity of this Riemann sum, approximating the area using rectangles. Well, in this video, we're going to be taking a look at better approximation techniques. We can start off with the idea of basically estimating using rectangles, and the midpoint rule was pretty good. But let's compare that with a couple other different strategies for numerical approximation. Now let's just remember that when we have a function y equals f of x, we're trying to find the area underneath that using the definite integral. Well, this goes back a little ways, and we approximated using rectangles. We subdivided the interval from a to b into n equal subintervals with a width of delta x equal to b minus a over n. And then each interval has endpoints xi, where xi are these values, a plus I delta x, for I equals 0 to n. So with I equals 0, x naught is just equal to a, and with I equal to n, xn is equal to b. And in between we have x1, x2, x3, x4, all the way up to xn minus 1 as being little endpoints of each of these subintervals in between. Now, if we just choose any xi star somewhere in each of those subintervals, then we can plug those in and have this Riemann sum, f of xi star delta x, summing from I equals 1 to n. Now, we did look at left and right endpoints in previous videos, but we found that the midpoint rule is actually probably one of the better ways to go. Now, the midpoints are just halfway between the endpoints of each of these subintervals. For midpoints, we'll just use the notation xi bar, because bar typically means an average, and that's exactly what we're doing here. We're going to be taking the average of the left endpoint, xi minus 1, and the right endpoint, xi. So we'll just add those and divide by 2, and that gives us our midpoints. And so we can call this the midpoint rule. The midpoint rule with n subintervals, let's just say, is mn. M for midpoint, n because that's the number of points we're going to be plugging in here. And that's given by delta x times f of x1 bar plus f of x2 bar, so on and so forth, adding up all of these midpoints until we get to the nth and final midpoint. Well, that's our midpoint rule written out without the sigma notation. Remember that this is typically better than using left or right endpoints. We can use right endpoints and take the limit as n goes to infinity as maybe one of the easier ways to get the actual value, but midpoint rule with a fixed number n is probably better than just using left or right with a fixed n. But let's introduce a new rule here, the trapezoid rule. And the trapezoid rule is nothing more than taking the left endpoint rule and the right endpoint rule, adding them together and dividing by 2. For the trapezoid rule, well, we're going to take the area given by using left endpoints, Ln, and take the area given by using right endpoints, Rn, find the average of those two. Now, if you take Ln and Rn, add them together and divide by 2, what you actually get here is the trapezoid rule, Tn. And you can see, by adding them and dividing by 2, we end up with delta x over 2 times the sum of x naught plus 2 times f of x1 plus 2 times f of x2 plus 2 times f of x3 until we get to our second to last little subinterval endpoint, 2 times f of x of n minus 1 plus a single f of xn. Now the trapezoid rule is quite convenient because left and right endpoints are very easy to find just by using the formula for xi equals a plus I times delta x. Those are fairly easy to calculate, and now we can plug those into the function here as long as we remember this 1, 2, 2, 2, 2, 2, 1 kind of pattern, and then we will multiply by delta x over 2 to get the trapezoid rule approximation of the integral. Now let's visually compare midpoint rule and trapezoid rule and see if you can kind of understand that both of them do a fairly good job of approximating the area under a function. Suppose that we wish to calculate this blue shaded area under the function y equals f of x. Now I'm going to just start off with only n equal to 3 subintervals. So that's not going to be a very good approximation, but it will give you a good idea of how the midpoint rule and trapezoid kind of approximate area with different shapes. Midpoint rule, well, if we're going to divide this interval from a to b into 3 subintervals, I can just draw those vertical bars here, and each of those subintervals has a width of b minus a over 3. Now, the midpoint here, I'm going to be picking a point halfway in between each interval and approximating the area by using rectangles of a height of f of x I bar. My first rectangle here looks like it's an overestimate because that midpoint seems to be about at the highest point of that particular function there. My second rectangle looks like a very good approximation. I have part of that rectangle being an under approximation, part of that rectangle being an over approximation. And here at the bottom, it looks like it's a little bit more of an underestimation just because of the curve of that function. The more that this function is curved, you can see that I have more potential to get an error. So the midpoint rule is just going to be adding up the area of those 3 bars, and you can see that I'm not perfect, but I'm also probably not too bad. As far as the trapezoid rule goes, we are only using left and right endpoints. So I will start off once again here by dividing up into 3 subintervals, and I will only using the endpoints, left and right. Now, my first subinterval here, I'm going to approximate that using a trapezoid. So looking at that trapezoid, you can see that is most definitely an underestimate of the actual area. But here, where the function doesn't seem to have quite as much curvature, well, that is definitely a very good estimate of the actual area. And my last trapezoid seems to be a bit of an overestimate. Overall, they both seem to do fairly decent jobs of approximating, but that could really depend on how curved my function is. Now, because of this idea that the curve of a function is causing more and more error, we have another method here called Simpson's method. With Simpson's method, or Simpson's rule, what we're going to be doing is instead of having rectangles with flat tops or trapezoids with flat line segments, we're going to be approximating this curve using small little parabolas. So Simpson's rule is quite different. If we were to start off with only using 3 subintervals, then we could start off more or less the same way here. 3 subintervals would give us our area divided up into 3 equal components. Now, if you want to try to come up with the equation of a parabola that fits this first subinterval, you actually need to have 3 points, because a quadratic has ax squared plus bx plus c, giving us 3 different coefficients. So with Simpson's rule, in each of these subintervals, we're going to take a third point, and we can approximate using a little parabola in that section. So we're going to need an additional point here in that first subinterval. In our second subinterval, again, we have 2 endpoints, but we want to fit a parabola to that subinterval. We're going to need a third point in the middle. Now that is also a parabola there, and you might see a little bit of error, but hopefully not quite as much as just using a straight line segment. But again, we're going to need an additional point here, somewhere in the second subinterval. And in the third subinterval, we'll also need an additional point, and we're going to fit a parabola to that little segment as well. So in the end, instead of just thinking about n as being equal to 3 subintervals, it might make more sense here where I actually have to calculate x0, x1, x2, x3, x4, x5, and x6. So this might make more sense to actually say this is Simpson's rule with n equals 6. I've got x0, x1, x2, x3, x4, x5, and x6. You're going to see that one restriction with Simpson's rule is that n will always have to be an even number, because every subinterval will actually need to have a point in the middle. Now, Simpson's rule will beat out midpoint and trapezoid simply because you can see that I am actually allowing curvature to not cause additional error. Now, the calculation for Simpson's rule is a little bit more complicated to derive, but it turns out to be a fairly nice, straightforward formula, much like midpoint and trapezoid rule. Once again, here's the formulas for the midpoint and trapezoid rule, but now you'll also see Simpson's rule, Sn, and that's given by delta x over 3, and we have this interesting pattern of plugging in those different points into the function f of x naught plus 4 times f of x1 plus 2 times f of x2 plus 4 times x of x3, and we'll continue on with this 4, 2, 4, 2 pattern, but because n is always even, we'll end up with 4 times f of xn minus 1 plus a single f of xn. And again, all of these little formulas here on the side are important to always know whenever we're approximating using rectangles, trapezoids, or Simpson's rule with parabolas. Delta x is always going to be b minus a over n. Xi are always going to be the endpoints of each little interval, and that's just a plus I times delta x, starting at 0 and working up to n. And for midpoints, we're always going to be taking the average of left and right endpoints of each subinterval. Now, the only confusion here is with midpoint, n equals 3 means we have 3 sample points or 3 subintervals. Trapezoid rule, n equals 3, again, we have 3 subintervals, but you are actually plugging in 4 points because you will be starting at x0 and working up to xn. In Simpson's rule, when we have n equal to 6, well, that was actually because we had 3 subintervals, but we have an additional point in between. And that means you're actually plugging in 7 points, starting at x0, working our way up to x6. So let's try calculating each of these values, and then we can also take a look a little bit more about which of these has what kind of error in approximation. All right, in this example, let's take a look at the definite integral of the cube root of 1 minus cosine x from x equals 0 to x equals pi. Now right away, if you want to try to calculate the exact value of this, you may be a little bit confused as to what method you're going to try to use here. It doesn't look exactly like a normal substitution is going to work here, and trying to be somewhat creative with maybe rationalizing or something doesn't look like it's necessarily going to be easy either. So why don't we try midpoint rule, trapezoid rule, and Simpson's rule, since this is a definite integral. We'll use n equals 4 on each of these so that it's pretty easy to compare the 3 different results. Now remember, we always have to calculate delta x as b minus a over n, and we have to calculate x0, x1, x2, x3, and x4. Well, let's start off with the midpoint rule, and midpoints are going to be halfway between each of those different xi's. So the first thing we have to remember with midpoint rule is simply just delta x, which is pi over 4, multiplied by f of x1 bar. All right, well, that's halfway between 0 and pi over 4, so that would be pi over 8. And then f of x2 bar, x2 bar is halfway between x1 and x2. That gets us 3 pi over 8. Now remember that these are always equally spaced by pi over 4, so we could always just take pi over 8 and add pi over 4. Pi over 4 is simply 2 pi over 8. So pi over 8 plus 2 pi over 8 is 3 pi over 8. And we could continue a pattern from there. Add another 2 pi over 8, and that gives us 5 pi over 8. And last but not least, our last one will be 7 pi over 8. That makes it a little easier to calculate the midpoints once you've gotten that first one. So you can simply just add delta x every time. And each of these values need to be plugged into our function. Our function f of x is equal to the cube root of 1 minus cosine x. So while it's a little bit tedious to calculate each of these 4 values, we don't really have much other choice. Trying to integrate this any other way and getting an exact value isn't going to be easy either. I'll let you try this out for yourself and see what you get as a result. You should end up getting something of the form 2.8534 with several decimals after that. Well, let's just see about rounding all of these maybe to 4 decimal places and see how close they all actually are. Remember that n equals 4 isn't really that many different points. Now remember, for the trapezoid rule, we have to take delta x over 2. And we have a pattern of using these endpoints x0 all the way to x4, where we have f of x0 plus 2 times f of x1 plus 2 times f of x2 plus 2 of f of x3 And finally, when we get to x4, we have simply just f of x4. And plugging in 5 of these different points into that function, we can approximate this to 4 decimal places again. Try this out for yourself and see what you end up with. And you should end up with 2.7404 approximately. Now, last but not least, we'll look at Simpson's rule with n equals 4. And remember that with Simpson's rule, we have delta x over 3. And once again, a very interesting looking pattern. F of x0 plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3, and finally f of x4. That 1, 4, 2, 4, 1 pattern. Plugging each of those 5 points into our function, making sure we have the coefficients 1, 4, 2, 4, 1, and don't forget to multiply by delta x over 3. That should give us something around 2.8004. You can see that they're all fairly close. They're all roughly around that 2.8 region, with trapezoid being the lowest, the midpoint being the highest, and Simpson's being somewhere in the middle. Now, if you want to understand kind of roughly why we have trapezoid being a little lower than the other two, you might want to try to graph this function. Now, luckily, I've already done that in Maple, because it's not exactly an easy one to try to sketch by hand. So let's take a look and see what kind of shape this gives us. Here is that function, the cube root of 1 minus cosine x, and I'm graphing that from 0 to pi. So you can see where those rectangles would be. Now, this is not only always increasing over that interval, but it's also concave down. And that's going to tell you a little bit about why we're going to get some errors in our approximation. Let's see what these kind of estimations would actually look like if we were to graph the rectangles, trapezoids, and little parabolic segments for Simpson's rule. Okay, well, here is the midpoints. You can see that for each of these rectangles, they are centered at pi over 8, 3 pi over 8, 5 pi over 8, and 7 pi over 8. And for every rectangle, I have part of the area sticking above the function and part of it being below. And for every one of them, there always seems to be a little bit more sticking outside of the curve than missing from inside the curve. And so it will give us a little bit of an overestimate because it is concave down and increasing. All right, well, now let's take a look and see what the trapezoid rule gives us. Here is the trapezoid rule. Now, because I'm using straight line segments connecting each of the endpoints of the subintervals, these are always going to be straight lines that lie below the curve. And again, because that is monotonically increasing, it's never decreasing over that interval, and it is concave down. So all line segments are going to be a little bit lower. So there's no choice here. The trapezoid method has to give us a little bit of an underestimate. Now, what about for Simpson's rule? All right, well, here's Simpson's rule, and don't be confused. I have partition equal to 2. But remember, that's just the number of subintervals, not the number of points. For every subinterval, you can see I'm also including another point here, and I'm estimating this curve using a parabola. And that's not going to be great in certain areas where I have this particular function bending a little differently than a parabola can, but overall is very, very close. In fact, it's probably still just a tiny bit of an underestimate, but not by very, very much. So with that in mind, you can see where the errors are going to be coming from. Here, if we have a function that has concave down or concave up, that's going to give us a little bit more of a problem where rectangles don't do a very good estimate. Same thing goes with the trapezoid rule. If our function has a lot of concavity, either up or down, we're going to see that line segments are always going to be under or over estimates. Now, with Simpson's rule, if this was a parabola instead of the cube root of 1 minus cosine x, then a parabolic function can be, of course, approximated with parabolas, no problem. We actually have to go a little bit further beyond that. We actually have to go look at higher derivatives to kind of understand how badly curved this function is compared to a parabola. That gives us some formulas for finding the maximum amount of error on any one of these 3 different rules. So let's go back to the notes here and finally just give some error bounds for these 3 different methods. When we're talking about error, we're really thinking about what the difference is between our estimate and the actual value of the integral. And that means that the error could be positive or negative. If the estimate is a little less than the actual value, then that is a negative error. And if our estimate is above the actual value, then that's a positive error. What we want to look at here is what is the maximum amount of error, positive or negative. Let's just assume we're going to take the absolute value and figure out what the maximum value is for the absolute value of error for these three different methods, midpoint, trapezoid, and Simpson's rule. Now, if you remember, we really find we get a lot more error with midpoint and trapezoid rules if our function is strongly concave down or concave up. So really it has a lot to do with the shape of the function. So let's suppose that the maximum amount of concavity, up or down, positive or negative, is less than some constant. So the point where our function has the most concavity, or the largest sort of curvature of that second derivative, let's say that that maximum number is k at any point in the interval from a to b. Well, if we're taking a look at the maximum error in the midpoint rule, we say that the maximum amount of error, that's this absolute value of em, is less than or equal to k times b minus a cubed all over 24n squared. So you can see as k is larger for curves that have a lot more concavity, then we get more potential error. And also we see n in the denominator. As we use more and more rectangles, as n goes to infinity, eventually this error becomes closer and closer to zero and we get the actual value. Now, what about the trapezoid rule? Well, as it turns out, the trapezoid rule is actually a little bit more affected by the shape of the curve. Here you can see k over 12 instead of k over 24 for the midpoint rule. So that means for any value of k, we actually get a little bit more potential error in the trapezoid rule, as long as we're comparing the same number n for midpoint and trapezoid. When we start thinking about Simpson's rule, though, we know that Simpson's rule really has no problem when we're using parabolas to model a function that's concave up or concave down, so long as our function is fairly close to being a quadratic. So that's why with the Simpson's rule, our maximum error bound actually has to really involve a higher level derivative. For Simpson's rule, let's assume that the maximum value of the fourth derivative in the interval is this value, k. So now we're really not too concerned whether or not the function has concave up or concave down points in the interval. We're really more concerned about how quickly the concavity is accelerating in one way or another. That second derivative of the second derivative. That will give us a maximum error bound on the error for the Simpson's method. And right away, you can see here that in the denominator, we also have n to the 4. So you can really think as the number of little points that we're using on the curve to form those parabolas. If we were to double that, well, then we're going to be taking our error and we're going to be scaling that by a factor of 1 over 2 to the 4, which is 1/16 of the total amount of error. So this really approaches the actual value very, very quickly as n starts to increase. And that's what makes that Simpson's method kind of our best rule out of the three. Now, there are other approximation techniques that you can use for definite integrals, but Simpson's method here suffices pretty much for as long as n is relatively large and the function is not overly complicated with higher derivatives. The midpoint trapezoid rule, it may be a little bit easier to understand or to calculate, but Simpson's rule is going to be our kind of our go-to when we're looking for estimating the error or estimating the value of some kind of definite integral. This doesn't really help, unfortunately, for indefinite integrals, but that's where you may have to use a computer algebra system to see if you can find the actual antiderivative of those kind of functions that you can't integrate with our classic techniques. Now, with this behind us, we can kind of get a sense that really any kind of integral, we should be able to use some kind of method, whether it's a technique that will allow us to get the exact value, or whether it's a technique like one of these where we can approximate the actual value of this definite integral. Thanks for watching, and I'll see you again in the next video.